All right, today we're going to dive deep, I mean really deep, inside the atom. We're on a mission to uncover the secret life of one of the universe's most vital and, honestly, most interesting particles, the electron. It's unbelievably tiny, it's literally everywhere, and it holds the keys to some of the most amazing things in our universe. So, let's get into it.
So let me just start with a question for you. What in the world could possibly connect the invisible pull of a magnet, the crazy bright colors of a neon sign, and the light from a star that's billions of miles away? It sounds impossible, right? But the answer to all of it is our tiny friend, the electron. And today, we're pulling back the curtain on its secrets.
Okay, so the first secret power we're going to talk about is the electron's magnetic spin. Now, this isn't just some random twitch. Nope, this is a built-in fundamental property, and it's the very source of one of the most powerful forces in nature, magnetism.
I want you to picture every single electron out there as a tiny little top that is spinning, constantly, forever. And this spin isn't just for kicks. As it spins, it generates its very own tiny magnetic field. So yeah, in a very real way, every electron in the entire universe is its own little micromagnet.
Now, electrons in an atom aren't just a big chaotic mess. They're actually super organized into these things called orbitals, and they have to follow a really strict rule. It's called the Pauli exclusion principle. You can just think of it as the ultimate buddy rule. If two electrons are going to share the same space, they absolutely cannot spin in the same direction. It's a cosmic law. One has to spin clockwise, the other counterclockwise. Period.
So what's the big deal about this rule? Well, when you've got paired electrons, their opposite spins create these two little magnetic fields that point in opposite directions. And what happens? They perfectly cancel each other out. The result is the atom as a whole is not magnetic. But if an atom has a lone unpaired electron, there's nothing to cancel out its spin. That single spin creates a net magnetic field, and suddenly the whole atom becomes magnetic. This is the simple but profound difference between what we call diamagnetism and paramagnetism.
And here's where it gets really cool, because you can see how this tiny property scales up to huge effects we see every day. Diamagnetic materials, the ones with all their electrons paired up, are actually weakly repelled by magnets. Then you have paramagnetic materials with those lonely unpaired electrons, and they're weakly attracted. But then you get to ferromagnetic stuff like iron. In these, the unpaired electrons in all the atoms actually team up and all align in the same direction. And that's how you get the powerful permanent magnets that stick to your fridge.
But spin is only one of the electron's tricks. Its next secret is all about how it deals with energy. And it doesn't move like anything we're used to in our big world. It makes something called a quantum leap.
So every electron has what you could call a home base. We call it the ground state. It's the electron's favorite spot, its lowest energy, most stable position. But if it gets zapped with some energy, maybe from heat or a particle of light, it can jump up to a higher energy level, an excited state. So think of the ground state as its comfy couch at home, and the excited state is this, high energy party. It's fun, but it's unstable. It can't stay there.
So here's how that little journey works in 4 steps. First, some energy, like a photon of light, slams into the electron. Second, it doesn't climb up a ladder, it just vanishes from its spot and instantly reappears at that higher excited state. That's the quantum leap. It's like teleportation. But that state is totally unstable, so it's only a matter of time before the electron falls back home to its ground state. And when it falls, it has to get rid of that extra energy it absorbed. How does it do it? By spitting out a particle of light, a photon.
And this is what it actually looks like. This chart shows what's happening inside a simple hydrogen atom. Now, the crucial thing here is that the light that gets released is not random at all. Its color, its specific wavelength, is determined by exactly how far the electron fell. Check out the Balmer series there. When an electron drops from energy level 3 down to 2, bam, it spits out a photon of very specific red light. Every single drop produces a predictable signature color.
And that brings us to the electron's third, and for today, final secret. That light it's spitting out, it isn't just some random flash. It's a unique, impossible-to-fake signature. You might even call it an element light fingerprint.
You see, because the energy levels, those rungs on the ladder, are totally fixed and unique for every single element, the possible falls an electron can make are also fixed. This means a sodium atom is always going to emit light of certain colors when its electrons fall, and those colors will be completely different from the colors that, say, a neon atom gives off.
I mean, just look at this. These are what we call bright line spectra. This is what you see when you take the light from an excited element and shine it through a prism. See how lithium has that really strong red line and then a few others? Now look over at strontium. Its pattern is totally different. It's like a unique barcode made of light. No two elements have the same one. It really is their fingerprint.
And this is so much more than just a cool science fact. It is an incredibly powerful tool. Just as our source says, this uniqueness is what allows scientists to identify elements in a mixture. We can look at the light from a star that's millions of light years away, analyze its light fingerprint, and know exactly what it's made of. All thanks to the little electron and its quantum leaps.
So, let's just quickly recap the electron's secrets we've uncovered. Its built-in spin makes it a tiny magnet, and that creates the magnetic forces we see all around us. Its quantum leaps between energy levels are how it absorbs and then releases energy as light. And finally, that very light it releases acts as a perfect, one-of-a-kind fingerprint, letting us identify elements anywhere in the universe. When you think about it, from magnetism to light itself, the strange behavior of this one single invisible particle shapes so much of the reality that we see and experience every day. It kind of makes you wonder, doesn't it? If this is the stuff we've figured out so far, what other secrets are they holding?